Good morning, everybody. Um, Today, I want to share some of my research results for vibration-based fault detection of two-stage planetary gear using atoms. First of all, I want to say the outline of today's topic. First, I want to introduce the background about this topic and the purpose why I do the research in this field. And the second one is two-stage fixed axis gearbox with atoms and the experimental results. In this paragraph, I want to share some of my experimental results and show some of our atoms results and to do certain comparison in order to capture the vibration signatures of the fixed axis gearbox. And the third one is the vibration signature of two-stage planetary gear using atoms. In this part, I want to show some of the vibration signatures which are not published before from atoms simulation results. And the fourth part is the joint time frequency analysis. So this one is a little bit new for me and a lot of engineers, and we use a 3D FFT from atoms results, and we will show unique vibration signature. And the last one is conclusion. First of all, I want to give you an introduction. Due to the nonlinearity induced by the combination of backlash and different teeth damage at different locations, the complicated dynamic behavior of the planetary gear are not thoroughly understood by majority of the engineers and even for the researchers. Because now there's, even if the most sophisticated theory models can only simulate the first stage planetary gear, and very few publication describe the gears with the defects, especially the dynamics behavior. That means the whole dynamic systems response from theoretical model. And from FEA, another way is to do FEA. But for FEA, there's another limited. That one, FEA focus on the local analysis. It's very hard for FEA to do the whole system dynamics analysis. So in this way, our team found a way to use atoms. Maybe in majority of the engineers or the researchers will think about the atoms focus on the rigid body. But actually, in our case, we model majority of the part as a rigid body, but for the teeth, we make that as a elastic body by carefully choose the parameters. For example, the stiffness, the force exponent, and the penetration depth, and the damping coefficients, etc. And in this way, we will be very accurately simulate the dynamic behavior of the teeth of the gear. So other part, temporarily, we just model as a rigid body, and we carefully choose the atom simulation parameters for the constraints and bearing resistance torques and some other key parameters in order to realistically simulate the gearing transmissions operation. So I'm going to show the comprehensive frequency domain analysis of the dynamic contact force. So in this way, we want to capture the unique vibration signature, which is called modulated sidebands. The last one is joint time frequency response. So in this way, we will see when the system just start, how the vibration contents just change in a short time period. So this is a very unique technique in gearing application. So first of all, I want to, we didn't use the Adams machinery because I want to accurately simulate the profile of the gear in order to make sure our results are accurate. So what we did is we used MATLAB to write the involute profile of the gear. So in this way, I can control how many points on the involute points I want. So this is the example of our MATLAB results, and this is SolidWorks model. We use SolidWorks in our university. So, and this one is accurately modeled by CAD. So, and the next step is to carefully choose all of those parameters. For example, now we model the teeth as the elastic body. So at the same time, we model the use the nonlinear contact force, which is like this. So of course, we got to choose K, D, E, and all of those parameters. So, and how do we choose that? Actually, we do two ways. The first one is compare our results with the experimental results, which we already finished. In the next several slides, I'm going to explain some of our results, to show some of our results to you. And another one is we actually compare our model, use a simple pair of the gear compared with the published papers. So in this way, we got to carefully adjust all of those parameters. So here is our example problem. So I don't have time to explain this much, but it's published in our publication in ASME conference. So you will see at the last page of my presentation. So now what I want to show is our two-stage fixed axis gearbox in our lab. Here is the gearbox, and if you look at here, we have the accelerometers, which is installed on the top of this is a bearing. There are two bearings there, so it's on the top. We actually carefully choose the location of the accelerometers in order to capture the strongest signal. We grew the accelerometer in many places. We try here, we try immediately above the bearing. We found out this is the best place to measure the vibration in response, the dynamic response. And here is our CAD model. And here is the top view. So there are two-stage fixed axis gear. And here is the exploded plot. So I got to explain a little bit here. Even if we show the gear, the bearing locations, we actually in our simulation we didn't simulate the bearing because at that time we don't have the Adams machinery. We don't have the beautiful bearing library. So in this way, if we want to simulate the bearing, we got to do the rolling bearing or ball bearing. There are a lot of contact there. So that's why we didn't simulate. But in the future, we will simulate about the bearing and also the gear. So recently, we only simulated the gearing system. Okay, here is our the practical gear box. So, and we have four sets of the gear. One is the perfect one. This is the perfect one, and another one with the chipped teeth, with the missing teeth, and another one is a crack on the shaft. I believe it's like that. So we actually do a comprehensive experimental. We got a comprehensive dynamics response from our test rig. This test rig is called Gearbox Dynamics Simulator from Spectral Quest. Then we use here is our gearbox. This is a motor. Then here is a control box, and here is actually there's a laser, a key phaser here, and this is coupling. So here is our gearbox with a brake. And we connect this system with the computer software called LDS Doctrum. So we have the laptop here to get the signal um, from the accelerometer on the top of the gear. So if you look at here, this is old, our old experimental, our old accelerometers we put on here, but we found out the signal are not good. First we thought it's good, but actually it's not. So we moved to the top. We change different accelerometer here. So here is an example of our experimental results. This is a vibration results. And of course, in industry, majority of the engineers use the frequency response in time domain. So our input speed is at 17 hertz. So the output is the power spectrum. So this is the results. And actually, this is a very sensitive system. And if you see the power spectrum is only 10 to negative 6. So that one is very small, but we really capture some of the signal. See, look at the 1/6 of the gear mesh frequency of the first stage peak show up, and also this is the inner race of the ball path frequency of the bearing show up, and this peak is dominant. We actually later found out there's some damage for the bearing, which makes sense because the bearing inner race. So, and this makes sense because this one becomes the dominant inner race ball path frequency of the bearing. And there are a lot of small peaks. For example, 1/3 of the gear mesh frequency of the first stage. And actually, once we get all of those results, and we got to analyze what's wrong happened for the system. We first noticed this, then we dismantle our equipment. We found out, oh, there's a defect on the inner race of the bearing. So anyway, this is the example problem from the experimental results, and you will see many peaks show up, and they show up not by accident. It's because of the system, the dynamic behavior of the system. For example, the gear mesh frequency of the second stage and the gear mesh frequency of the first stage. And it's super harmonic, and the combination of the gear mesh frequency of the second stage plus 2 multiply F3. F3 means the intermediate shaft velocity. So and outer race ball path frequency. So we actually see there's a little bit defect on the outer race as well. That's why it's it's super harmonic of the outer race ball path frequency peak show up, and also the combination of this show up. Actually, we don't understand some of the part because this is the experimental results. That's why we need the simulation to see what kind of defects show up. So now, what we did, so this is the table. We identify all of those peaks. It's a combination of the gear mesh frequency and first stage, second stage, and the shaft speed and the ball path frequency of the bearing. Then, in order to understand if there's defects of the system or not, we use atoms. We use atoms to simulate all of those kinds of results. This is the very early stage of the simulation. We finished that in 2010. So, and this is only for two-stage planetary gear with the gearing system. So if you look at the the simulation results, you will find out the gear match frequency of the second stage show up, the first stage show up, and also 1/3 of the second stage gear match frequency show up, and all of those peaks and its super harmonic and the combination, all of those, and we show 1,000 hertz, the total 1,000 hertz. But in our experiment, we only show 700 hertz. In the first, before all of those peaks, actually, atom simulation results match with our experimental results if we look back. So you will see majority of the peaks match. So in this way, we will say, oh yes, our atoms simulation results do reflect some of the practical dynamics behavior. Since this system, we didn't simulate the bearing system. Just like I mentioned before, because there's a lot of contact problem, so it will take a while for us to do that. So now with Adam's machinery, so we can add our bearing actually from industry. That is very good. In the last of the slides, I will show some of the results. We will, in the future, we will incorporate all of them. Hopefully, we will capture almost exactly, not exactly similar like this experimental results. We will try our best to do that. This is what we expect. Okay, so now let's go to our two-stage planetary gear model and the parameters. So atom simulation parameters. In this case, we want to use our parameters and to study the two-stage planetary gear. So this is our two-stage planetary gear. The right-hand side are our design parameters and atoms simulation parameters. So we have the module is 3 millimeter and the pressure angle is 20 and the face width is 10 millimeter. And we have 18 teeth on the sun at the back. At the sun here, sorry. So this sun gear has 18 teeth and 33 teeth on the first stage of the planet, and 33 teeth, 30 teeth on the second stage teeth, and the first stage ring 84 and the second stage 81 teeth. So, and this is a example of the damage. Actually, some of them say, oh, this damage is not, it's not realistic. But actually, this is our we finished that last year. So this year, we can make the damage more realistic in CAD. Before, frankly speaking, we don't know how to model that. That's why we use that. Actually, it doesn't matter because that one we only want to capture the vibration signature. So now we can make the teeth more realistic in our future job. Okay, so here, based on our design parameters, so we calculate we do the two speed. One is 48 hertz, another one is 62 hertz. In order to say at a different speed and to say if they show the similar vibration pattern, if the crack happens at certain teeth. So then we calculate. Of course, there's involves a lot of sophisticated calculation. Use the corresponding planetary gear formula. So then the carrier speed, the planet speed, the second ring speed, because the first stage ring is fixed. So, and gear mesh frequency of the first stage, gear mesh frequency of the second stage, and the Huntington frequencies. So we calculate all the possible velocities here. Then in this way, this will help us to understand the system better. Then now this is a typical Adams simulation results. So here is a time domain response. Of course, in Adams, we convert that in the post-processing. If you go to the plot, it will show convert to FFT plot, because usually in industry use FFT. So here I want to show the simulation results about this case. So if you see we apply a speed, a step speed, just simulate the motor, gradually apply the speed from 0 to 100 radians per second. So in a duration of 0.4 seconds. So, and we have the crack on the thumb, every other third teeth. So there's a crack on the thumb. That's why gradually when you see the speed increase, so there's a certain impact force show up. And this is a typical video simulation. So now here, what we will do is to show the perfect gear, the perfect system, the gear system. So for the perfect gear, then you will see we get the atom simulation between the sun and the planet, the contact force. So you will see the gear match frequency of the first stage and the second stage, and its superharmonic and peaks show up, which makes sense. It's matched with all of those published, the publication. And the input is 48 hertz and another one is 62 hertz. So, and of course 62 hertz, the speed change of the gear match frequency of the first stage change. But the vibration signature, vibration patterns are similar. So, and now this is another one. We damage every third tooth damaged on the thumb. Maybe you guys might ask why every third teeth are damaged, because because according to the planetary theory, the first stage teeth we have 18 teeth, and the planet has 33. So the common factor between 18 and 33 is 3. So that's why if there's only one tooth is damaged, eventually every common factor teeth will damage. So that means the total 6 teeth will damage on the thumb. So in this way, if you look at that, the vibration pattern changes. So it's subharmonic, 1/3 of the gear match frequency, and 2 over a third. Gear match frequency, this is a show up, and it's subharmonic, and it's superharmonic. Still show up, and super synchronous of the first stage gear match frequency also show up as well. And similar pattern for the second, for the another speed here show up. So this is it's different from the perfect gear. So now, and what we do is we will see, we want to observe what happens for the every third teeth damage on the thumb, and the the same thing, sorry. The same thing, every third teeth damage on thumb, but we get the output. We get the output from the planet, and the ring. The previous one is we get the output from the sun and the planet, but now it's from the planet and the ring. So here, if you look at the vibration pattern, it's very similar. It's very similar like the previous one. But the interesting thing is if we increase the speed a little bit, so this 48 hertz is similar like the previous one, but if we increase a little bit, so you will see the gear match frequency of the second stage show up. So, and look, this is a gear match frequency, the difference of the first stage minus the second stage. And the rest of stuff are similar, but there's a small peak. So this is the gear match frequency, the sideband, modulated by the difference of the first stage and the second stage. Similar for the here, the sidebands here. So this is very unique for our case. So, and now this one is showing when we damage the sun, both the sun and eventually the sun, if the sun has a defect, of course, it will eventually damage the planets. So the planets should have um, 11, 11 teeth will eventually damage. So now we show the results between the sun and the first stage planet. So if you look at the vibrations pattern, say look at this 1/6 gear mesh frequency show up, all of those one, it's still subsynchronous, super synchronous vibration pattern will show up. And some of those small peaks disappear if the speed changes. But if you look at the magnitude, actually it's reduced for the peak compared with the sun gear damage only. Excuse me. So because the energy is distributed, it's modulated by the sidebands. So, but we will do more research how it changes if we have more damage. Now we didn't do the in-depth research, but this is a primary results. Okay, so now we got to talk about the joint time frequency of the gear system. So this is a perfect gear. Perfect gear, what we did is to apply an exponential step input. So with the torque 750 Newton millimeter in the duration of 0.3 seconds. So what we apply is we simulate the motor system. So it's gradually increase the torque. So then in this way, if you look at the x-axis is a frequency, and the y-axis is actually the time slice. So this time slice, we make that as very small. So it simulates when the system just start. Then if you see the frequency contents also change, the pattern look like that. Since this is our first time to show this one, actually, we don't know. We actually didn't do the in-depth of the research, why this change like that. The vibration contents in a very small, short period of time, so the vibration pattern should show like that. This is top view of this. This is without crack. Now this is with the crack on the sun. Every 30th are damaged on the sun. So we apply the same torque, but if you see in a short period of time, so the frequency contents show up and more peaks show up here, and this is top view, and this actually we say the energy is distributed because of the crack. So this is one pattern. So if we want to look more, so we can damage more teeth and to see how it changes. And now this kind of technology, joint time frequency analysis, is applied in rotor dynamic system, in rotating machinery in industry. But now this is our first time to simulate in for the gearing system. Okay, so in conclusion, we use the computer simulation to simulate the complicated gear chain to give the powerful insight to the engineer, which theoretical model or other methods cannot offer. So this is we feel very proud of these results because now, from my experience, we have a lot of contact with the General Energy. So before they call that as Bentley Nevada, that company. So they apply the health monitoring system in the wind turbine gearbox. They actually observe a lot of sidebands due to the crack, but they desperately need the modeling, what causes that. They have certain experimental results, but some of the engineer told us they only do that from the experiment, from their field. measurement, but they don't have the simulation because the FEA, it will take a while for them to finish. They couldn't get the results. So that's why this is our first time to provide this two-stage planetary gear simulation results, which theoretical model cannot model that and other methods cannot. So we do the primary research. And the vibration signatures for predicted tooth defects and damage can accurately model and simulate using atoms. Actually, there's a lot of in-depth, a lot of details about how to use atoms to simulate that. And of course, the most beautiful thing is the joint time frequency response. So I actually have a lot of simulation about this kind of results with different damage. So I believe this one will become most powerful tool for the diagnostic for the defects. And here I want to show you the simulation results for the bevel gear, because now this is one of my graduate students do that. So we have the test rig, and we compare our results with our experimental results. That one is good. So we publish one paper in Adams conference. If you have an interest, you can look at that. So now the only thing what we change is to make view flux. This is Adams, another powerful function to make the shaft like a flexible shaft. And also we add the SKF bearing into our system. So in the future, maybe in 2 months, and he will apply this technology for our two-stage planetary gear to see how it works with our two-stage planetary gear. So now if you see, we apply speed, gradually apply a speed to 40 radians per second. So it's gradually change. And we cut the keyway on the shaft as well in order to simulate the unbalance of the rotor system. So the beautiful thing is, if you look at here, when the speed is very small, so the unbalance is not obvious. But when the speed gradually increases, it causes the vibration oscillation, which makes sense because we make the shaft as a flexible shaft. So the view flux is really powerful tool for atoms, because you don't have to resort to FEA. There's an embedded solver to realistically simulate the whole system. And also the bearing. This is a bearing contact force response. And we didn't do the in-depth study yet, but we will do FFT analysis and to compare this one with our results, experimental results. I want to say currently there's slow results about the two-stage planetary gear. That's why we only show the atoms simulation results. If in the future, if some of you have an interest, we can do research. So, and I would like to, some of the results are shown in ASME conference in August. So this month actually in Portland. So you can look at this paper. Actually, Yijun has this paper. If you have interest, I can email you. And I would like to express my deep appreciation to Dr. Maher, my colleague, and Andrew Sommer. He is an engineer, my previous graduate student in solar turbine, and my graduate student, Yijun.Fan, and he do majority of the simulation. Thank you for your attention. Yeah, questions?
Okay, thank you, Professor Wu, for your very informative and interesting presentation. So before we go to the Q&A session, we have a few kindly reminders. First, if you have any question regarding the presentation or atoms, please use the Q&A to type down your questions. We will have them answered. And if you don't have question at the moment, please take a minute to answer the polling questions. Okay, so now let's go to the Q&A session. Actually, Professor, if you don't mind, you can just share the slide. You can
share.
Oh, you can just show the slide. Yeah, you just like this. You don't need to pass me the presenter. You can
Okay.
Okay. Yeah.
Okay.
So
Thank
we have
you.
our contact information listed on the slide with Professor Wu's email address and my email address. So if you have any, if your question is not answered today, or if you have further questions, please send us an email, and then we're glad to answer those questions for you. Okay, so the first question we had is, how did you verify the contact force resulting from your simulations?
Oh, that is a good question, actually. Uh, we cannot directly verify the contact force. So what we did is to do the comparison of our relative displacement of the gear with the published paper. Okay, I can show you another one. Oh, sorry, this is not correct. Okay, I didn't show here. This is my old presentation. Before, I want to show that. Here, we do one-stage gear chain contact. So we choose all of those parameters. Then what we did is to do the, okay, I will show this one. Okay, so here we do a pair of the gear, a simple pair of the gear from one published paper. So we apply an initial velocity 100 radians per second. Then there's a forward and backward impact. So what we did is we do the comparison of the magnitude of the impact. So we call that as a relative displacement with the published results to adjust our those parameters in order to make that match. So in this way, we will say, okay, that one might work properly. So this is what we did. But actually, in practically, we don't care that, at least now, we don't care that much about the contact force, because eventually we will do the accelerometers. We use the accelerometers to measure the acceleration. So we focus on the vibration pattern, what kind of the gear mesh frequency or sidebands. So this is what we care the most. So I hope this is what we do. Yeah.
Great.
Yeah. Thank you.
Thank you. And the second question is that can we export SolidWorks motion simulation to Atom's environment?
Export.
Yeah, I think I can take that question, Professor Wu. So so far as I know, we can definitely export the CAD geometry from SolidWorks to Atoms. And if you're talking about SolidWorks motion software, I think they're using Atoms. They're using a limited edition Atoms solver behind their interface. So SolidWorks motion and Atoms actually share similar solver, except for they have a limited capabilities. And also, I think you can definitely export your work from the SolidWorks motion to Atoms. And if you can use an ADM file, that would be feasible to do so. And the next question is, how did you perform the join time frequency analysis? What tool did you use? Thank you.
Oh, that's a good question. Yeah. When I give the presentation, I don't have time to show the detail. Okay. So in here, what we did is we just do the simulation, the same thing, just do the simulation. Then when you go to the post-processing, then you plot the time domain. You plot the time domain plot. Then on the top, there's a plot, the drop-down window in the plot, so you can choose 2D FFT. So 2D FFT, Atoms will automatically convert your time domains plot to this. This is called 2D FFT. Then you also can do the 3D FFT. So then you will do like this, 3D FFT. Then you can choose, the window will pop up. Then you will see the overlap. So there's a key point to get this plot. Actually, it took us almost 5 hours to get this plot, because you got to choose the overlap. The overlap means, I don't know the detail, but if you get the higher percentage of the overlap, for example, we get 95% the overlap, they will capture more detail like this. These small peaks will show up, but if you make this overlap, like 70%, then all of those peaks will disappear. So this is how we do the simulation. It's called 3D FFT. Then you can convert any of the time domain simulation results to joint time frequency response.
So in conclusion, it's that function is available in Atom's post-processor.
Yes, post-processor, yes.
Thank you. And the next question is how to correlate your simulation results to actual crack in the real world. Do you calculate fatigue life?
The fatigue life, you mean?
Yes, that's what she means, I think.
Oh, actually, no. This is another question. I want to make that clear. By the way, this is a very good question. Okay, so this is the difference between atoms and FEA. For the atoms, so you will calculate the stress and the strain. In this way, you can predict the life of the gearing system. So, but in my study, I'm the system engineer. So that means in our study, we focus on the whole system's dynamics behavior. So temporarily, we let another group of the engineer to do the FEA analysis. We call that as a local analysis. So in this way, you will look at if there's a crack, how it's propagate. But in my case, what we care the most is if there's a defect of the gear teeth, how these defects affect the vibration pattern of our whole system. That means because we have the sensor, right? The sensor is usually installed on the bearing location or on the gearbox. So if we see this kind of vibration pattern, can we tell if there's a crack or how large the crack is? But actually, it's very difficult to tell how large the crack is. So, and in GE law, they want to say, oh, yes, this vibration pattern, we see that. But how do we judge how big the crack is? Temporarily, they forget about how it affects the life of the system. So they want to say like that. Recently, in 2010, so GE introduced a concept which is called sideband energy ratio. So sideband energy ratio, what they did is, for example, they just add the sidebands, the 6 small sidebands near the gear mesh frequency, 1, for example. So now we don't have too many these small peaks. Add six of them, add them together, divided by the magnitude of the dominant gear mesh frequency of the first stage. For example, they consider this part. So they say this ratio is called sideband energy ratio. If this ratio is bigger than 1, it's there's a crack. So if it's even bigger, they say this is proportionally, this sideband energy ratio is proportional to the crack. But actually, we don't know if it's cracked or not. So they want to know more from simulation, but unfortunately, they don't have a simulation result. So this is only the primary step. We do that. So they have a certain experimental results. So there's no way for them to compare. So they told me, they said, okay, anyways, we have the monitoring system. So in other words, this is the focus. We focus on the whole dynamic system behavior instead of the local one. I
Okay.
hope I answer your question. Yeah, thanks.
Thank you. And the next question is, could you please explain the influence of a transmission error in analysis?
Please say again. Sorry. Yeah.
The impact of a transmission error in the analysis.
The influence of
The backlash?
the backlash or the transmission error?
Yeah, if you could explain more detail about what you mean by transmission error, it'd be easier for us to answer the question. Okay, the next question is, how do you identify the contact stiffness between contact pair? If the mating pair is of different material, what could be the resultant contact stiffness? That's the question.
Okay. Okay, so you want me to answer two questions, right? I want to make that clear. Two questions.
Yeah, that came from the same person. So how do you identify the contact stiffness? And yeah.
And the transmission error, right? Okay, so the definition for thank you. This is another good question. Good questions. So the first one is the transmission error. Actually, the transmission error includes many kinds of errors. For example, the manufacturer error, misalignment of the bearing or the gear, and also the defect of the gear, the crack on the gear, right? So, and I only in our study here, I only talk about the defect of the tooth. We only simulate the tooth damage. And we can also simulate the eccentric gear just by make the teeth a little bit larger for one gear. And the manufacturer error, that means, so as long as you can do that in CAD software, you can simulate, then we can transport into Adams to do the simulation. But now, currently, we didn't do that much. We will gradually do that by incorporate another errors in our research. So, and another question is the gear mesh frequency, gear mesh stiffness. That is another very good question. Actually, now I actually do gear mesh stiffness. It's a time varying. Variables. It's depending on the contact ratio of the gear.